Hi everyone, today we are going to talk about lessons 11, 1, and 2. Today's lesson starts actually on the supplemental note sheet, and then it will continue for 11, 2 in the book. Now on this note sheet, we see a couple of different things about our polynomial functions and writing our degrees. Now, sometimes you are writing and listing zeros just as an x equals. Sometimes they want us to leave these as a product of complex factors, aka in that factored form, as opposed to written like a 0 or written like an x-intercept. So we know if we have zeros at 3, 3, and 5, we can write this as x minus 3, x minus 3, and x minus 5 would represent our function in that linear factored form. Now, sometimes you might see this piece here represented as x minus 3 quantity squared, but when they ask us to write it as linear factors, we tend to just leave it in that factored form with each one written individually, although we do know that that means that there is a multiplicity there. Now, if we were going to sketch a graph of this, reminder, there are a couple things we need to consider. Number one, where are our zeros at? So we have 1 at 5, 1 at 3. Another piece here is if we plug in 0 for x and we look for that y-intercept, this time we would have negative 3 times negative 3 times negative 5, which would put our y-intercept at 0, comma, negative 45. So on this one, if we make this graph go down by 10 each time, that would put our y-intercept down here. And a reminder with this end behavior, it's a positive leading coefficient here. And through 5, we pass through. We have a multiplicity, though, at that 0 at 3. So then it would be shooting down to get to that y-intercept on this one. So it's a little rough sketch on that. In letter B, we have a 4th degree polynomial. This time, again, if we write it as a product of linear factors, we'd have x minus 1, x plus 1, x minus 3, and x plus 3 as our factors there. And again, if we want to sketch, there are basically two pieces here that we want to consider. Number one, our zeros at 3 and 1, as well as our zeros at negative 3 and negative 1. Our y-intercept this time, if we plug in 0 for x, we end up with a y-intercept at 0, comma 9. So 1, 2, 3, 4, 5. This time, if we have it go up by 2s, our y-intercept would be up here at 9. And again, positive leading coefficient makes this graph go upwards. Degree 4 means that these would also have to go up on either end. And then we have no multiplicities this time, so we're just passing through. Again, these minimum values here, for instance, might actually be shorter or taller. Maybe they are a little bit closer down here, and this one's a little bit bigger. But we see either way the sketch with the end behaviors, the zeros, and our y-intercept. Now, there is a theorem called the complex conjugate theorem. And basically what's happening is whenever you know you have a complex root, you know that the opposite sign of it is also going to be a root. So for instance, if 3i is a root, we know negative 3i must also be a root. So when we list our linear factors this time, it would be x minus 2, x minus 3i, and then x plus 3i. So essentially each time what this theorem is telling us is that if we have this root, it basically comes as a pair always with a positive I and a negative I each time. Or for something like part D, if we know 1 plus 2i is a factor, we know 1 minus 2i also would have to be a factor. So we would have x minus 1, x plus 3, f of x, equals x minus 1, x plus 3, x minus 1 plus 2i, and then 1 minus 1 minus 2i. So that these are both there. And this one you might see simplified a little bit. in that they might distribute that negative. So x minus 1 minus 2i, x minus 1 plus 2i on that one. Now, we've talked about before in some of the Delts math is being able to write then based on the picture of the graph. So this time we have a couple of zeros being given to us. We have a 0 at -3. We have a 0 at 0. And we have a 0 at x equals 2. And we have to be careful here because we have a multiplicity happening on this one. Multiplicity, because we have this bounce occurring here, this max at our 0 at 0. So we want to be careful of that. Because basically what's happening is as we start trying to write an equation for this function, we have our 3 zeros that we can put in factored form. But a reminder, if there's a multiplicity on this 0, okay, it's going to get at least squared, if not officially to the 4th or 6th power, but a minimum of an even degree power there. The other piece here is that we want to be able to solve for this leading coefficient. So we've talked about as well, another important piece of our puzzle here is that y-intercept. In this case, we have a y-intercept at 0, 0. And so what that means is we know our y value is 0 if we plug in 0 for our x value. Now this one is a little bit interesting when we start solving because, a reminder, anything that is, with 0, even if we have 3 and -2, we're multiplying all of this by 0. So it's essentially like it's, in a way, kind of canceling out. And if you divide that over, like our a value is really just a 1 here. Because what's going to happen is if we plug this back into our equation, that x minus 0 quantity squared we could just write as x squared. And we have the x plus 3 and the x minus 2. And a reminder that 0 being at 0 is kind of influencing that a value to just be 1, because when we have that 0 there, that's kind of forcing our y-intercept. But otherwise, we can work backwards and solve for that a. Now, a lot of that we've talked about before, but what about a little bit more with these complex zeros beyond the complex conjugate theorem? Well, if we start then on page 146 in our books, we see, again, these ideas of our zeros that are rational and but are not factorable officially because they're giving us these irrational numbers when we solve, but they're real, right? There is no imaginary, we're getting to answers. They just happen to involve a square root. So that's, again, what we have, that square root number is irrational. Versus having complex irrational numbers that are involving an I. So we have a complex square root, so it's imaginary and it's irrational, both happening because of that I. So again, taking the square root of the negative number, forcing that. So we see some examples down below here. For example, with example A, if we set this equal to 0 and square root, 5 is not a perfect square. In fact, we would just leave this as the square root of 5 when we break it down. But because of this negative, we have to put that I out front. And again, notice the instructions this time want us to write the function as a product of complex factors, aka you want that final answer in a factored form versus just writing out the zeros. It wants a certain notation. So this time it's basically asking us to do two things. Find the zeros and write them as a product of the complex factors. So for instance, this first one, we have x squared minus 8 equals 0. In this case, add over the 8, and when we square root, we would have x equals plus or minus the square root of 8. Now officially, 8 can be broken down. If we break this down as full as possible, the perfect square of 4 goes into it. That's 2 and 2, right? So that moves outside the radical This 2, though, did not have a buddy to move out with it, so it would stay inside. So this time our x values would be positive or negative 2 root 2. So that's kind of part 1, find the zeros. All right, and then the second part is write it in that factored form. So we would say x plus 2 square root 2 and x minus 2 square root 2 would be the product of the complex factors. Now, these both are real answers. They just happen to be imaginary or irrational, so no imaginary is necessary. Letter B, however, if we set that equal to 0 and try and start solving, we end up taking the square root of a negative number this time. So this time we need that positive or negative. The I is going to move out because we took a square root of a negative here, and we are left with the square root of 11 that does not break down like our example up above did. So again, if we're looking for just the zeros, we would say positive or negative I square root 11. Or if we write that in that factored format, you would see x minus I square root 11 and x plus I square root 11 for those two answers. All right, part C we'll leave for you. And otherwise, we are moving on then to example B. So if we notice down in example B, we have, again, some product of the factors. This time, we are looking at them, again, kind of X method style on this first example. What multiplies to be negative 14 adds to be negative 5, 2 and negative 7. And notice, again, anytime we have x to the fourth, x squared constant, we are able to kind of cheat the process and treat it like our normal factoring. However, because of that little pattern, these just become squareds instead of just x's. And then we can set each piece equal to 0 and write it as its factored form or use it to find the individual zeros. So if we see at the top of page 147, again, we have a couple more of these examples. So this first one is asking us to factor. So notice this is actually a difference of 2 squares. X squared minus 4 would be our A and our B values, and then x squared plus 4. Because again, x squared squared would be x to the fourth. 4 squared is 16. Well, officially, if we set each of these pieces equal to 0, we end up getting plus or minus 2, and then plus or minus 2i as our zeros. So to write these as complex factors, again, we would write this in that fully factored form of x plus 2, x minus 2, x plus 2i, x minus 2i would be the factored form. Our zeros then, we would just list as x equals positive or negative 2, positive or negative 2i. Skipping over B for now. In part C, we are looking to potentially group here. We take out a GCF to start, take out a GCF of the second piece, and notice we have two factors again, x squared plus 4, and then 2x minus 1. So the zeros this time, again, will come from setting each piece equal to 0. So we end up with, again, some complex factors, positive or negative 2i, or we have 2x equals 1, so x is positive 1/2 for that. So these would be our zeros. And then to write our answer in that complex form, x plus 2i, x minus 2i, and then you could either leave it as the 2x minus 1, or you could call it x minus 1/2. Again, either way you wrote that, these are the equivalent to each other. This would be your other answer. All right, our last example down here, again, we see this 4, 2. We can kind of treat this like we are factoring type 1, 6, and negative not 6 and negative 1, excuse me. We would end up with on this one negative 5 and negative 1 that multiply to be 5, add to be negative 6. So we'd have x minus 5 and x minus 1. The only difference here is because this is 4 squared constant, we make this a squared term. And as we set each piece equal to 0, this time we have to take the square root of a non-perfect squared. So we get x equals positive or negative square root 5. Over here, we square root, x is positive or negative 1. So again, there's a difference between our zeros here and writing our answer in that complex format where we have x plus, x minus, and then x plus 1 times x minus 1. Officially all 4 pieces. All right, our last piece here today is going to then talk about what happens when we want all of the values, real and imaginary, for these different functions, including, again, the negative parts. Before, when we only were looking for the reals, we would only focus on this part. However, what about this piece over here that we before were trying to find? This is going to give us our imaginary solutions when we have a sum or difference of 2 cubes. And in this case, we end up using our PAL, the quadratic formula, in order to solve the missing pieces on that, again, either from a non-factorable piece or, again, like the sum and difference of cubes, this piece will help us find those values. So a couple of examples here. In letter A, we have a non-factorable. Nothing's going to multiply to be 11, add to be 3. So this is where we want to use our PAL, the quadratic formula. So x equals, because we have A, B, and C, x equals negative b plus or minus the square root, b squared minus 4 times a times c, all over 2a. Now this piece underneath the radical becomes 9 minus 4 times 11, which is negative 35, and then all over 2. And we know that then this piece inside here that I would move out, we would have this square root of 35 inside. So officially, we end up with 2 answers. Okay, whatever negative 3 plus I square root 35 over 2 is, either the positive of that or negative 3 minus I square root 35 all over 2. All right, down in letter B, we can start by factoring out a GCF of 3x squared. And what this does is it at least allows us a little bit of a breakdown here. However, we still get then this non-factorable term here. So one piece we still have to be careful of is the fact that 3x squared equals 0. So x squared equals 0 when we divide over the 3. Square root, x is still equaling 0. The other piece is going to come from A, B, and C, plugging into the quadratic formula. Because again, x is going to equal this time negative b plus or minus the square root, b squared minus 4 times a times c, all over 2a, which this time is 1. And this time, as we solve, underneath, we have 4 minus 28. So negative 24 is underneath the radical. That is going to move out so that we have I on the outside. And then officially, the square root of 24 can break down to be our perfect square of 4 times 6 Those 2's are moving out with the I, and then we have a square root of 6 on the inside. And then last but not least, because this 2 can be simplified in both pieces, we can take 2 divided by 2, we get 1. 2 divided by 2 is 1i square root 6. So officially, our x has 1 real solution and then 2 of our non-real solutions, either 1 plus I square root 6 or 1 minus I square root 6. All right, thanks everyone for watching. I know it's a lot of info. We will work more with these imaginaries in class.